Imagine blasting off from Earth, aiming for the tiny speck of Mercury glowing near the Sun. It looks so close on a star chart, just a quick hop across the inner solar system, right? Wrong. Mercury has laughed at our spacecraft for decades. We reached Venus and Mars faster, even flung probes past Jupiter and Saturn. Yet Mercury sat mocking us until 1974. And even then, we barely scratched its surface. Why? It's not just the blistering heat that melts circuits or the sun's glare. The real villain is something far more sinister. The sun's gravitational grip turns any approaching spacecraft into a runaway bullet. Slowing down enough to orbit Mercury without burning every drop of fuel is like trying to parallel park a sports car while it's being sucked into a black hole. Today, we're diving deep into the brutal physics, engineering nightmares, and mind-bending solutions that make visiting every planet in our solar system, from scorching Mercury to frozen Pluto, an epic saga of human ingenuity against the universe's harshest rules. By the end, you'll see why sending humans to Mars isn't just hard. It's a multi-generational puzzle that makes the moon landings look like a Sunday drive. Stick around, because the surprises in how we finally cracked Mercury's code and what waits on distant moons might just change how you see our place in the cosmos. Let's launch. Let's start with the shocker. Venus is Earth's true closest neighbor at about 40 million kilometers at closest approach. Mercury comes second, averaging closer than Mars most of the time. Shortest distance approximately 77 million kilometers versus Mars's typical 88 million kilometers, though Mars dips lower every 26 months. Yet Mercury became the toughest early target. We sent Mariner 2 to Venus in 1962, Mariner 4 to Mars in 1965, Pioneer 10 to Jupiter in 1973. Mercury? We waited until Mariner 10 in 1974, and it only flew by 3 times, mapping just 40% of the surface. Then, for 30-plus years. Why? 2 killers, temperature and speed. Mercury's dayside hits 430 degrees Celsius, hot enough to melt lead. Spacecraft need massive sunshades, oriented perfectly so instruments stay in shadow. But the bigger issue is orbital mechanics, and the sun's gravity accelerates anything nearby to terrifying speeds. Rockets alone can't brake effectively without carrying absurd fuel loads, which means less room for science gear and skyrocketing costs. Engineers minimized weight ruthlessly. Every extra kilogram demands more launch fuel, turning missions into budget black holes. For decades, no elegant solution existed. Then, in 1985, MIT nuclear physics grad Chen-Wan Yen proposed a wild route using gravity assists. Instead of a straight shot, the spacecraft would loop the sun 15 times, stealing and shedding velocity via flybys of Earth, Venus twice, and Mercury 3 times. Picture this real-life analogy. You're in a car trying to match a fast-moving train. Accelerate too aggressively relative to the ground, and you're still fast compared to the train. But time it right, and your relative speed drops to near zero at the perfect moment. That's gravity assist in action. Planets act as slingshots that tweak trajectories with almost no fuel. Our Messenger launched in 2004, a compact, approximately 1-ton probe with a sun shield. Solar panels cleverly used as partial sails against solar wind pressure and a main engine for final capture. It traveled 7.9 billion kilometers over 7 years before entering orbit in 2011. Orbits were eccentric, 200 to 15,000 kilometers altitude, to dodge heat radiated back from Mercury's surface, which acts like a giant mirror. The sun appears 7 times brighter there. Messenger mapped the whole planet, analyzed composition, and spotted hints of water ice in permanently shadowed polar craters, shocking for a world so close to the sun. It ended by crashing into the surface in 2015 when fuel ran out. Now, Bepi Colombo, ESA/JAXA, continues the work, arriving around 2025 with even more advanced instruments. Personal insight. This mission proves humanity's creativity shines brightest under constraint. We didn't overpower the problem with brute force. We danced with gravity. It reminds me of how early sailors used ocean currents instead of fighting them. In space, physics isn't the enemy, it's the map we must read perfectly. To make this vivid, consider the engineers behind Messenger staring at simulations for years, tweaking flyby angles by fractions of a degree. One miscalculation, and the probe would either sling past Mercury forever or plunge into the sun. It's like threading a needle at 100,000 kilometers per hour. Now, contrast that with Mars, the planet everyone dreams of colonizing. Elon Musk and NASA talk about it constantly, yet no humans have gone. Why? Distance is the root of all evil here. Even at closest approach, approximately 55 to 59 million kilometers every 26 months, it's still a heliocentric journey, not a quick low Earth orbit hop. Low Earth orbit, LEO, where the ISS lives, is just approximately 400 kilometers up, like driving from one city to a nearby town. The Moon is approximately 380,000 kilometers, about 1,000 times farther, conquered in days with Apollo. Mars? A minimum distance is roughly 1,000 times the Earth-Moon gap, or 1,000,000 times a typical ISS trip. One Mars round trip equals 1,000,000 space station runs in scale. Real story. Think of Apollo 17, the last moon mission. It used the massive Saturn V, 3,000 tons, to send approximately 50 tons toward the moon for approximately 12 days total, with 2 astronauts on the surface for 3. For Mars, envision 6 astronauts on a 900-plus day mission, 174 days out, 539 days stay for optimal return alignment, 201 days back. Supplies balloon approximately 150 times due to duration alone. Add radiation shielding, interplanetary space lacks Earth's magnetic protection, spare parts for everything that breaks, no quick resupply like ISS, and fuel hundreds of tons just for acceleration, deceleration, and return. One vivid example, proposed in situ resource utilization, ISRU, on Mars extracting water ice or CO2 to make fuel. Sounds smart, but we've never tested full systems at scale. Until then, every drop comes from Earth. One compared to the Space Shuttle, 15 to 25 tons to orbit, or Ariane 5, approximately 20 tons. You'd need 10-plus Saturn V-class launches just for one crewed mission's infrastructure, assembled in orbit like a cosmic Lego set. The entire Apollo program used only 9 Saturn V's. Weightlessness adds horror. Months in zero-G weaken bones, muscles, and hearts. No rotating habitats exist yet to simulate gravity. Psychologically, Earth becomes a faint star. Real-time talk is impossible, up to 20-plus minute delays one way. Confinement in a tin can for 2.5 years? That's not adventure, it's a pressure cooker. Radiation could cause cancer risks we still don't fully mitigate. My analysis, we're not almost there for Mars. Apollo was a sprint with clear goals and massive Cold War funding. Mars demands a marathon with sustainable tech we haven't fully built. Optimists say mid-century with enough budget. Realists point to unsolved fundamentals like reliable closed-loop life support and heavy-lift reusability at scale. The lesson emerging: exploration scales, non-linearly small distance jumps explode complexity. Jupiter, easy to reach thanks to its massive gravity, but orbiting or diving in is brutal. Arrival speeds are so high that probes zip past unless braked with rockets. No solid surface atmosphere transitions to crushing liquid metallic hydrogen under pressures that pulverize anything. Radiation fries electronics. Galileo exceeded its design limits. Only one probe, Galileo 1995, dipped in, lasting 58 minutes before heat/pressure destroyed it at approximately 153 degrees Celsius and 22 times Earth G-forces. Story: Cassini, en route to Saturn, snapped stunning Jupiter images, revealing small storm cells invisible from Earth. Juno currently orbits safely, mapping magnetic fields and auroras, but will eventually crash to avoid contaminating icy moons like Europa, potential subsurface ocean. Future missions like JUICE target those moons for habitability clues. A Saturn, even farther, requiring nuclear RTGs because solar panels starve in weak huygens. Extreme cold demands insulation. Cassini-Huygens, arrived 2004, was the star. Huygens landed on Titan in 2005, revealing a frozen world with methane lakes, rivers, and rain carving Earth-like landscapes, yet at minus 179 degrees Celsius. Enceladus sprays water geysers from a subsurface ocean, hinting at possible life ingredients. Cassini ended by plunging into Saturn in 2017 to protect those moons, gathering final atmospheric data. Uranus and Neptune, the ice giants, get ignored. Uranus's 98-degree tilt creates bizarre 42-year polar day/night cycles. Imagine a pole in constant sunlight for decades, then darkness. Temperatures plunge to minus 224 degrees Celsius. Only Voyager 2 flew by both in the 1980s for speed. Communication lags, nuclear power wait, and decade-long team continuity, knowledge loss across generations, as seen in lost Apollo-era expertise, kill proposals. Neptune's violent supersonic winds and Moon Triton, captured Kuiper object with cryovolcanoes and likely ocean, recently tipped NASA interest toward it over closer Uranus. Personal commentary: these distant worlds show how exploration priorities shift. Early missions chased firsts. Now we chase habitability subsurface oceans on Europa, Enceladus, Titan, Triton. Planets themselves are harsh. Their moons might host life's building blocks. It's a humbling pivot. We're not conquering worlds, but probing for cosmic kinship. Pluto, once the 9th planet, now a Kuiper belt dwarf at greater than 6 billion kilometers. New Horizons, 2015, flew by after endless cancellations. Distance, power decay in RTGs, budgets. It revealed nitrogen ice plains with recent geology, possible subsurface water, and a thin atmosphere. No orbit, just a high-speed snapshot, before heading deeper. Proxima Centauri, nearest star at 4.24 light-years. Voyager 1, 17 kilometers per second speed, 76,000 years. We need 10,000 plus kilometers per second for reasonable trips. Chemical rockets, impossible fuel ratios. Concepts like laser-driven sails, breakthrough starshot, or nuclear pulse could send gram-scale probes in decades. But humans? Generational ships or breakthroughs? Away. It forces us to ask, are we mature enough for interstellar leaps? From Mercury's gravity dance to Neptune's frozen mysteries and the abyss to Proxima, the solar system isn't a playground, it's a gauntlet of physics, energy, and time. We visited via clever assists, nuclear hearts, and resilient machines, but human footsteps beyond the moon remain distant. The clear lesson: true exploration demands patience, collaboration, and respect for limits. We succeed not by ignoring constraints, but by innovating within them, using gravity as an ally, miniaturizing where possible, and prioritizing sustainable science over flashy firsts. As we eye Mars or icy moons, remember, every probe teaches resilience. Humanity's greatest voyages start with understanding why they're hard. The universe rewards the curious who plan for reality, not fantasy. What barrier will we crack next? Thanks for watching. Like, subscribe, and comment your favorite planetary puzzle. The cosmos awaits, but only if we're smart enough to reach it.